Hi everybody and welcome to this webinar. I'm Gio from University Pompeu Fabra in Barcelona. So what's the story with UAV cellular communications? Well, the outline of this talk is very simple. We'll try to follow the recent story of UAV cellular communications. Thus, the structure of the talk is chronological. So we'll go from 4G to 5G and to 6G use cases, requirements, and enabling technologies. Before we start, let me say thanks to all the people that have contributed to the interesting results that have been produced in the last few years. In particular, I would like to give a special mention to Adrian from Huawei, Sandeep, Marco, William, and Seunjung from NYU, and Angel from UPF. So let's get started. Why are UAV communications so important and in the hype? In many developed countries, still a visual line of sight operation of UAVs is mandatory. However, a beyond visual line of sight operation of UAVs will likely be legalized in many countries in the upcoming years. So, this is going to enable a range of new use cases and new business opportunities, for example, like the ones shown in this slide, but many, many more than that. So we will have multiple possibilities to control these drones or UAVs autonomously. We could use, for example, satellite communications, we could use high altitude aerial platforms, or we could use a dedicated ground network. Another option, which is very appealing, is to reuse the existing cellular infrastructure. And that is very appealing, as we'll see, and it's the focus of this talk. So it comes as no surprise given all the use cases and applications that UAVs have been making the news. This makes UAV communications research even more exciting, and I guess that's all. That's why we're all here. So here's some recent international press coverage of my joint work with some colleagues from Mississippi State University, for example. So let's go back to the technical stuff. We're going to take the perspective of a mobile network operator, which sees UAVs as potential users of its network. So what would the pursuit of revenue of such operator be? Well, I'm listing two bullets on this slide. The first one is that the operator can handle this beyond visual line of sight command and control traffic. Command and control is being denoted as CNC in this talk. So imagine that the operator is able to somehow handle this traffic that allows for autonomous flights of drones. Then in that case, it would open new markets and opportunities for revenue. Of course, besides that, the usual payload traffic can also be handled by an operator. So if we have UAV generated payload similar to current data traffic for ground users, then there are opportunities for operators there too. And of course, the dream, as I mentioned before, would be to reuse the existing ground network infrastructure or the one soon to be deployed for ground users anyway. But the reality is that this might not always be possible, and that operators might have to prepare the ground to accommodate aerial users, meaning they might need to upgrade their network and do some sort of an investment to be able to accommodate both ground users and aerial users. There's another way of seeing UAVs when trying to integrate them in a network, and it's seeing UAVs as base stations. So the figure you see at the right of the slide is actually a prototype of the project Future Cell by Nokia Bell Labs of a drone base station. So the dream in this case is to use UAVs as mobile base stations or radio access nodes, and perhaps enhance network performance through a dynamic on-demand repositioning of such base stations. The reality again is that there are many challenges to be overcome for that to be true. You need to identify the optimal locations of these drones. They have limited flying times, there are strict regulations, and you need to provide reliable control. And in many cases, you probably need to provide a wireless backhaul as well if you really want these drones to be untethered and therefore mobile. So again, the problem boils down to creating a reliable link from the ground network to the base station, to these drones, whether they're acting as base stations, therefore relaying the signal, or whether they're end users themselves. And for this reason, the 3GPP, the standardization body, has started focusing on the use case of UAVs as users first. So the first goal of the 3GPP was to determine up to what extent ground cellular networks can provide reliable communication for UAV users. So let's see what was done. Here's a standardization timeline. So the work of the 3GPP on UAV communications started in March 2017 with the definition of a study item phase on enhanced LTE support for aerial vehicles. The general objective of this study item phase was not to directly change the standard, but rather to understand whether there were communication issues and to identify technical solutions to address them. So such study item was concluded in December 2017, and simultaneously a work item phase was defined to introduce modifications to the standard using the most promising techniques that were identified in the study item phase. After these, other work items have been proposed by several companies, but they are not confirmed yet. So what the 3GPP did first was determining the traffic requirements of UAVs when these are connected to a cellular network. That's clearly the first step to be done. And two types of traffic were identified, as I previously mentioned. The first one is what we call the command and control traffic or link. This is both an uplink and downlink type of traffic, and it has several requirements that can be particularly strict in terms of latency and reliability. The throughput requirements are not so high, we're talking about 60 to 100 kilobits per second, but they have to be met reliably. And then there's the usual application data traffic, similarly to what happens for ground users. The difference is that for drones, it is expected that the data traffic would be mostly uplink, for example, for drones doing video streaming. Of course, if we want to evaluate the performance of UAVs when connected to cellular networks, it is of paramount importance to have a good channel model. So there was an effort by the 3GPP to specify an accurate channel model and also the type of UAV deployments that will have to be considered. So for example, at what speed these UAVs would travel and at what height they would fly. You see those summarized in this slide. The channel model was updated to account in particular for the height of transmit and receive nodes. So the channel model, which was originally in 38901, was generalized to aerial users, accounting for the height of these users. So once all these scenario parameters were defined, system level simulations were performed by many companies to characterize the performance of LTE cellular networks when they're serving both ground users and UAVs. And many observations were made. In this slide, I'm summarizing the three observations that I deem of major importance. So it was found out that UAVs are likely to generate harmful uplink interference to ground users. The reason for that is that UAVs fly high above the clutter of buildings in an urban area, for example. Therefore, they see many base stations in line of sight with favorable propagation conditions. So a signal transmitted by a UAV can interfere severely to many cells and can be overwhelming when compared to the signal transmitted by a ground user. Then drones also receive downlink interference from a large number of ground base stations. That means that when we talk about downlink, drones turn from offenders to victims. So they can be victim of interference from many base stations. It was shown that drones flying at about 100 meters height can see base stations for about 10 kilometers. So all these interference signals, if the network is particularly loaded, can be again overwhelming and then can cause a very poor SINR at the drone user. Also, drones are likely to experience a degraded mobility performance for multiple reasons, because they're highly mobile and therefore they can be very fast, and because the association to base stations, as we will see, relies on secondary lobes. That's because drones are higher than the base station, so they do not see the main lobe of a base station, but rather the upward pointing secondary lobes, and these have notches and peaks of power. And third, because as I already said, being high, they see many base stations, so it's highly likely that every now and then they'll see a base station that provides a better signal than the current one. So for all these reasons, some measures had to be taken, trying to solve the three main issues listed in this slide. So let me explain a little bit better the problem of cell selection and the mobility management issues with drones. So if you look outside, you probably see some base stations in the city where you live. They pretty much look like a vertical panel, which is slightly down tilted to illuminate a certain cell. And the antenna pattern resulting has a main lobe as shown on the left of this figure, and several secondary lobes. So if the user is on the ground, like the blue drone represented in this figure, it could be just a normal user, a ground user. This drone is probably going to always fall within the main lobe of the antenna pattern of a base station. And as you move away from the base station, still the drone is going to be within the main lobe. However, if you look at the red drone, which is flying higher than the base station, for example at 50 meters or even more, then this drone will never fall within any main lobe of any base station. Obviously, it's going to see only secondary lobes, and as you can see, by moving, it would move from one secondary lobe to another, and therefore the antenna gain will be fluctuating a lot. So this is shown on the figure on the right, where we see the antenna gain in dB versus the distance between a drone and a base station. So basically what we're doing in this figure, we are imagining that the drone moves away from a base station, basically following the arrows that we have on the left, and we try to observe the antenna gain, how this fluctuates. So if we look at the blue curve, there's a smooth transition. That is because the drone is at a height of 1.5 meters, so on the ground, basically like a ground user, and therefore the antenna degrades, but the antenna gain degrades, but it degrades smoothly. It has a normal trend, let's say. Of course, we should disregard what happens for very small distances, because these are not practical. A user would never be that close to a base station, so we should look at what happens from 50 meters onwards, and that's pretty smooth. However, if we look at different heights, for example, we consider a drone at 50 meters, so we look at the dash red curve, then in that case the trend is completely different. We see there are a lot of ups and downs, a lot of fluctuations in the antenna gain, and the drone is never in the main lobe of the base station. So this is going to cause problems, because the drone will probably associate to a base station that is far away, as we will see, and as the drone moves, it's going to see very sharp fluctuations in the signal amplitude. In this slide, I try to clarify a bit better what I said in the previous one. So then again, a little bit more on cell selection for drones. Let's look at the figure on the left. In this case, we take the perspective of the drone again, and we want to see what's the distance to the serving base station. So we're plotting the distribution of such distance. Once again, if we consider a drone at 1.5 meters, so the blue curve, this distribution looks pretty normal. The serving base station will be somewhere between 30 meters and 700 meters, and the trend is pretty smooth. However, if we take the example of a drone flying much higher, for example at 150 meters, so if we look at the green dashed dot curve, then this curve exhibits a very different behavior. It looks like a staircase, and all these steps of the staircase actually correspond to secondary lobes. So this is the first observation. And of course, the second observation is that the serving base station in general is much further away. We see that it's about 500 meters away compared to the blue curve. Now we can discuss the same phenomenon by taking the perspective of the base station. So now we're looking at the figure on the top right. In this case, we place ourselves on the base station, which is at the origin of this plot. It's a tri-sector base station, and we try to see what drones would associate to our base station. Those are the red dots shown on the figure. So as you can see, this is for a drone at 150 meters. There are some regions which are shaded in green, and they are delimited by blue circles. They are clearly defined. So all the drones that are associated to our base station fall within those regions. They are delimited by concentric circles. And it's not a continuum. They are clearly identified regions, and each of those, guess what, corresponds to the secondary lobes of the antenna pattern that we saw before. So that said, I already anticipated that drones are victim of interference in downlink when connected to the cellular network, especially when they fly high, because they see a lot of interfering base stations in line of sight. This is what I'm trying to show you in this plot. So the plot on this figure shows the SINR per PRB, per physical resource block, means on a certain time frequency resource for a drone, as a function of the height of the drone. So let's focus for simplicity on the black curves of this plot. You see obviously that the trend is decreasing, so the SINR gets worse and worse as the UAV height grows. That is because of interference, clearly, and you also can compare this to the minimum modulation encoding scheme SINR required to actually achieve any non-zero rate, and these black curves all fall below that. We have three black curves because they represent the best SINR, the 5% best, the average SINR, and the 5% worst. But we see that once the drones are, for example, above 150 meters, even the best drones fall below the minimum modulation encoding scheme threshold. So high drones cannot achieve the command and control target rate that we have set, which, if you recall, was between 60 and 100 kilobits per second. So once all these problems were observed, in the last plot, I took actually quite a pessimistic scenario, which is a fully loaded network. So it's probably the worst case where all base stations interfere to the drone. But in general, this problem exists and it was observed by the 3GPP. So everybody realized that some solutions had to be implemented. So here is a list of the standardized solutions in LTE Advanced. So the first one relates to the problem of interference in uplink. So the UAV generated uplink interference. In that case, the solution was found to be uplink power control. So the conventional power control used in cellular network is what's called the fractional power control mechanism. In that case, basically what you do is you compensate up for a certain fraction of the path loss. It's actually quite a simple concept. Imagine that you're using a microphone. The closer you are to the microphone, the more you lower your voice. And as you go away from the microphone, then you can speak louder. So it's basically the same thing. But what's important is that for UAVs, because they are non-conventional users and they see very different propagation conditions, the two parameters that are typically used, which are called alpha, a path loss compensation factor, and P0, which is a range extension parameter, that had to be adjusted. So new UAV specific parameters were introduced in the standard. Also, new signaling was introduced such that the UAV could basically communicate to the base station and report if its height was above or below a certain threshold, and that is very useful for the interference, same as signaling for interference detection. So in that case, a UAV basically can report to a base station if it's receiving reference signals of a certain power from a certain number of neighboring cells. That means, for example, hey, I'm flying quite high, I'm seeing a lot of cells, I'm seeing their signals quite strong, that is a problem, so please, we should do something for interference mitigation. So all these solutions are very useful. There are some more. So the ones I'm showing on this slide are related to subscription-based access. So this is a framework to help prevent non-authorized cellular connection of UAVs, and this is done through new signaling, right? And finally, for mobility, a new radio resource control signaling was introduced to facilitate, for example, flight plan communication. What does that mean? Imagine that the UAV already knows where it's going. It can tell the network beforehand, such that the network finds the best way to offload the UAV to other base stations as it moves, thus facilitating the handover mechanism. So in this slide, I'm listing some references in case you're interested in going a little bit more deeper into what I've been talking about. These are all 3GPP documents that explain and show a lot of measurement campaigns and simulation results related to what we just said. So we saw 5 main outcomes of the 4G work item phase that finished actually in September 2018, so about 2 years ago. But the 3GPP standardization work hasn't stopped there. So new UAV use cases were identified, corresponding requirements were also identified for 5G new radio, and as we will see, there are some technical solutions that we have thought about to try to address these requirements, meeting them. So here I'm going to mention some system aspect studies. So these system aspect studies are defined by a technical specification group of the 3GPP. So you can see the figure on this slide shows the timeline. We are about release 17, so work is being done for release 17. And so here I'm listing two main areas of work. The first one is trying to define enhancements for UAVs connected to cellular networks. So define new service level requirements, new KPIs for new applications, both industrial and public. Also, there has been work on remote identification of UAVs, and this has to do with requirements for authorized bodies, for example, traffic control, to determine the UAV identity and its controller. Let me summarize some of the new use cases and requirements just to have an idea of how more demanding these are getting, and therefore we need new technology to meet them. So there are many use cases that have been defined. Here I'm listing only three of them. One is high resolution video live broadcasting, so again with more requirements than it used to be in for 4G. Radio access through UAV, that means UAV as base stations or relays, so providing network access. Also autonomous UAVs controlled by AI, and the requirements of all these use cases and many more that have been defined, of course, vary substantially. But we can say, for example, that application data would require up to 120 megabits per second per UAV with 20 millisecond latency. Command and control will have to be very reliable depending on the application, also supporting very high speeds. Also, positioning will be required for applications other than navigation with a very high accuracy. If you're interested in these new use cases, then you can find them mainly in these two documents that I'm listing on the slide, the Technical Report 22829 and the Technical Specification 22125. So we've seen that as we move from 4G to 5G, new use cases for UAVs are being defined, the requirements for the corresponding wireless links are becoming more and more demanding. So I will now discuss how two key 5G new radio technologies, which are massive MIMO and millimeter wave, which we're all familiar with, can actually help meet these new requirements. So let me start with 5G new radio massive MIMO. So the idea is to use massive MIMO, which is being rolled out anyway for supporting ground users, to enhance support for UAVs connected to cellular networks. So in order to show the potential of using massive MIMO to serve UAVs, I'm going to define four different scenarios such that we can compare them side by side. The first scenario I'm talking about is basically a simple single user mode, a single user scenario. So there is no massive MIMO here. This is very similar to the plot I showed earlier, where there was a lot of interference and the SINR was degrading with the UAV height. So in this case, as you see in the figure, each base station, each sector has an 8x1 array of cross-polarized elements, but there is only one radio frequency chain. That means that only one user can be served on each time frequency physical resource block. The second scenario I consider is what I call massive MIMO. So in this case, in a massive MIMO mode, as you can also see in the figure, base stations can do beamforming, okay? So we are equipping base stations now, just for example, with an 8x8 array of cross-polarized elements, but this time with 128 radio frequency chains. That means the fully digital precoder is possible. So base stations are able to spatially multiplex several users on each physical resource block. We assume the base stations are employing zero forcing precoding and combining in downlink and uplink respectively. And of course, channel state information has to be acquired in order to point beams towards users. And we assume that there's a realistic CSI acquisition with pilot reuse 3. That means that users exploiting channel reciprocity in TDD mode transmit sounding reference signals to base stations such that base stations can estimate the channel. And these pilots, these sounding reference signals, are being reused every 3 cells. So there will be pilot contamination, as I will show you. Since we'll see that massive MIMO does very well, but there is room for improvement, I will also discuss possible upgrades. So here I will mention upgrades that are possible at the UAV side. So what if we equip UAVs with a 2x2 adaptive array of omnidirectional elements, even just with one radio frequency chain? Well, if we do that, as you see in the figure, UAVs could perform very precise analog beam steering towards the serving base station. This could be highly beneficial because they could focus on the desired signal and they could filter out basically interference coming from other directions. We'll see how this benefits. And finally, a very smart way of using multiple antennas is doing null steering. So in this case, again, the upgrade is at the network side. Base stations still have massive MIMO arrays, but instead of just doing beamforming, they also do some interference suppression. So this is useful because they can spatially separate non-orthogonal pilots transmitted by different UAVs. So basically they can suppress interference in the channel estimation phase. And they can also place radiation nulls, as you see in the figure, during the data transmission or reception phase towards or from vulnerable out-of-cells users. We'll see that this is very beneficial, particularly for UAVs, because a UAV, when it's flying high, sees many interfering base stations. So if some of these base stations do suppress interference towards that UAV, the possible margins for SINR gains are very, very high. But let's see that. So we start with massive MIMO, conventional in downlink. In this case, let's assume that the channel state information has been acquired perfectly, just to have a benchmark. So in this plot, I show you the distribution of the rate for UAVs for the command and control channel in downlink. So if you recall, the target here was 100 kilobits per second. And I'm showing you the distribution of the rates by changing the UAV height. So you have different curves for 1.5 meters up to 300 meters. In this case, 16 users are being specially multiplexed. So things are getting much better here compared to the case shown earlier for 4G, where the SINRs were really bad. So in this case, you see that we actually get non-zero rates, and most of the time, the target of 100 kilobits per second is actually achieved, and for all heights. So why is that? There are three factors mainly. So the first one is that the SINR for drones is improved because there's a beamforming gain from the serving base station. The second reason is that nearby base stations are pointing their beams towards their respective users, and obviously the majority of these users are on the ground, so most of the beams are pointing down, therefore there's less interference towards the UAV. And three, on top of the SINR gains, there's obviously a linear capacity gain because now spatial multiplexing is being done, so many devices are being multiplexed at the same time, therefore there's a rate gain, linear one. However, the story is a little bit different when we consider realistic CSI acquisition. So if we account for the effect of pilot contamination, that's what this figure shows by comparing the rates for ground users in black and for UAVs in red in downlink, in the case of perfect CSI and in the realistic case of pilot reuse 3. So the perfect CSI case is represented by solid lines, whereas dashed lines represent the realistic case of pilot reuse 3. So in this case, we didn't fix the UAV height, we just distributed it uniformly as the 3GPP suggests between 1.5 and 300 meters, okay? And we place one UAV per cellular sector. So we see very clearly that pilot contamination degrades the performance of both drones and ground users. For ground users, there's a 50% median loss, and for drones, it's pretty much the same. So why does that happen in downlink? So we know that in downlink, UAVs suffer interference, but ground users are not supposed to suffer any more interference than they would usually do without drones. However, because the channel is being estimated in uplink, in massive MIMO, that's where drones are very dangerous because they create pilot contamination to ground users. Therefore, ground users see their performance degraded in downlink. So the conclusion of this is that massive MIMO is great. It's made a big deal of a difference compared to a single user case that we saw earlier, but massive MIMO alone might not be enough in fully loaded networks, so we could do better. And if you remember, I had two more proposed scenarios and upgrades, so we're going to see a comparison of those approaches side by side. So let's consider the UAV downlink again. And let's see what's the percentage of UAVs that achieve a rate above the threshold of 100 kilobits per second for command and control. But let's do that by comparing different approaches. So we have 5 in this figure, each one has a different color. So we go from a single user approach, no special multiplexing, nothing fancy. Then we have a single user with AA UAV, it means UAVs with adaptive arrays. So we have upgraded the UAVs. Then we have Massive MIMO in green. Then we have Massive MIMO with adaptive arrays of the UAVs. That means that base stations have Massive MIMO arrays, and UAVs also have small arrays for analog beam steering. And finally, we have Massive MIMO with nulls. That means, in yellow, that base stations have Massive MIMO arrays and they perform not only beamforming but also interference suppression. So they place nulls, right? Well, simply, we can see that as the UAV height increases, so we go from the left to the right, well, the performance goes down. Obviously, the percentage of drones that meet the 100 kilobits per second requirement goes down pretty fast. That's obvious because we know that the higher the drone is, the more interference it receives. However, we see that out of the different approaches, the yellow one, Massive MIMO with nulls, seems to be the most promising one. So we could conclude that Massive MIMO seems to be the key for reliable command and control in highly loaded networks, but interference suppression seems to be the one that provides the largest gains. So it could be actually desirable to employ Massive MIMO base stations, but also equip them with interference suppression capabilities. Now, just to conclude the study of Massive MIMO, let's take a look at the uplink of UAVs. In this case, we know that UAVs in the uplink are actually generating interference because they see many cells, so they could jeopardize the performance of ground users. However, if you have other UAVs in the system, UAVs can also interfere each other. So this is why on this slide I'm showing the performance, the rate, both the mean and the 95% likely rate, which can be a proxy for a worst case, let's say, as a function of the number of UAVs that we have in each cell. So obviously, as we expect, the more UAVs we have in a cell, the more the performance degrades because UAV cause a lot of interference to each other. Then again, I'm comparing different approaches. So if we follow the legend, we have a single user case, which performs very poorly because there is no beamforming and interference can be overwhelming. Then there's a Massive MIMO approach, which provides very large gains for the usual 3 reasons that we know. SINR is improved because of beamforming, a little bit less interference is received, and 3, there's a capacity gain thanks to spatial multiplexing. However, once again, we see that Massive MIMO with nulls is the most recommended solution. So interference suppression to remove the severe inter-UAV interference. So if you found these results interesting and you want to read more about them, here is a list of some publications from me and my colleagues that are related to what I just presented about Massive MIMO. And also in this book, you can find some of the things I've been discussing so far and actually much more. It's a book that is being published just now these days. So after discussing the potential of Massive MIMO, now I would like to talk about another key 5G new radio technology and whether and how it can be leveraged to provide high capacity links to cellular connected UAVs. I'm obviously talking about millimeter wave. So with millimeter wave communications, the dream is to exploit the availability of large bandwidths, and in the case of UAVs in particular, the possibility of having line of sight transmissions, because if UAVs fly sufficiently high, then they would not suffer from the obstruction of buildings. Also, ideally, an operator again would want to reuse 5G millimeter wave terrestrial infrastructure that is being deployed currently to serve ground users, also to support UAV users with high capacity links. The reality is, of course, always slightly different because in practice one must actually evaluate the coverage and the rates that would get in urban areas where there are possible blockages even for UAVs. On top of that, terrestrial base stations are usually down tilted. They are targeting ground users. So would we need to deploy extra base stations dedicated to UAVs? And in all of this, there's a lack of standard defined channel models. So although a lot of channel modeling effort has been made, the 3GPP channel model is not calibrated for millimeter wave. So what we propose to do with some colleagues is, first of all, define a new channel modeling methodology for millimeter wave UAV communications. So this new approach is based on a two-stage generative neural network. So it's a machine learning based approach where we feed a data set obtained from ray tracing. We use Remcom's wireless insight tool. One could also feed measurements to the neural network, but to begin with, we use a data set obtained from ray tracing. And in this, we consider two different cell types. We consider street-level terrestrial base stations, like in conventional 5G new radio deployments, and rooftop-mounted aerial base stations that could potentially be deployed dedicated to serve UAVs with millimeter wave links. Of course, other types of base stations are not precluded, because the approach is general, and as I said, one doesn't necessarily have to feed ray tracing data, could also feed measurements. This model is publicly available at the link that you see at the bottom of this slide. So let me explain briefly how the neural network works. The approach is actually rather innovative. It's a two-stage generative neural network. So why do we have two stages? We want to determine the parameters of the channel, of the propagation channel. So the first stage of the neural network is going to tell us basically whether a link is likely to be in line of sight or in non-line of sight. Then the second stage, given the output of the first stage, so line of sight or not, is going to tell us everything about each path, in particular the path loss, the delay, and all the angles of arrival, departure, and elevation of arrival and departure. So if we take a closer look, in the first stage, the input, as you see on this slide, is a vector u. U contains information on the distance between the UAV and the base station, and the type of base station, C, the cell type. This could be terrestrial base station, at the street level, or rooftop mounted, what we call the aerial base station. Of course, one could have other models of base stations. What's the output of this first stage? The output is a link state, as I already said, S. So it's line of sight or no line of sight. It basically gives you the likelihood of the link being in line of sight or no line of sight, and then you sample this probability. Then the second stage takes the link state as an input, and again it takes the vector u, which contains the distance between the UAV and the base station, and C, which is the cell type once again. The output of the second stage actually consists of many parameters, because for each path between the UAV and the cell, we would like to know the path loss of that path, so the attenuation, the delay in order to combine the phases constructively or destructively, and as I said, all the angles of departure or arrival, zenith of departure and zenith of arrival, so 4 angles. So we obtain the distribution of these angles, and once again we sample them to obtain the parameters. So experimental data on UAV channels at millimeter wave has been limited. So that is why we employed a powerful ray tracing package to feed and train our neural network, which is Wireless Insight by Remcom. So what we did was generating data at 28 gigahertz. To generate the data sets, we considered 4 city sections, the cities of Tokyo, Beijing, London, and Moscow, that have different sizes, that have distinct types of terrain, buildings, and foliage. You see them represented on this slide. So what we did is we also differentiated different environments. Why did we do that? This is standard practice. If you are familiar with the 3GPP model, you know, for example, that the 3GPP classifies environments into urban macro, urban micro, suburban, rural, etc. So in this case, also to test the validity of the model produced by our neural network, we classified into 2 different environments. The first environment is based on the data from Tokyo and Beijing, which feature high-rise buildings with some wide open areas and parks. And the second environment consists of the data from London and Moscow, where there are more low-rise buildings of different densities, of course. So one could extend this, but we found the definition of these environments very insightful, because As I will show you later, one can see how accurate the model is within a certain environment and between different environments. Right, to produce our data, again, we placed two different types of base stations. Terrestrial base stations, which were placed on streets at approximate height of 2 meters, just like typical 5G new radio millimeter wave microcells. And aerial base stations, which were placed on rooftops, typically about 30 meters above the street level. These are supposed to provide additional coverage to UAV, but this is all to be verified. It's actually the purpose of this research project. UAVs, on the other hand, were placed at different heights, 30 meters, 60, 90, and 120 meters, to see what happens as we change the height of the UAV. So in this slide, I'm going to show you the conditional probability of a line of sight link. Okay, and this is plotted as a function of the distance to the base station, both horizontal and vertical, meaning elevation. We see two figures. The left one refers to the Tokyo-Beijing environment, and the second one refers to the London-Moscow environment. They are analogous. So what can we observe from these figures? We see that there's a very good match between the empirical distribution, meaning the data, and the model, right? So they're displayed side by side, and there's a very good match. Also, if we look at the figure on the left, we see that for higher UAVs, the line of sight probability is higher. So if you increase the elevation, then the line of sight probability is higher. For terrestrial cells, we see that these are often blocked by buildings. The probability of line of sight is smaller compared to the case of aerial cells. For aerial cells, the probability of line of sight is higher for higher drones and for drones that are further away. So what I mean is, if you increase the elevation of the drone or you increase the horizontal distance of the drone, then aerial cells can provide a slightly better coverage. A slightly better probability of line of sight compared to terrestrial cells. If we look at the figure on the right, so the London-Moscow case, well, as we already said, there are lower buildings in the London-Moscow environment. That means that there's a higher line of sight probability. We see this reflected clearly in the plots on the right of this slide, in particular greater distances, and this is both valid for both terrestrial and aerial cells. So this slide shows actually some very interesting phenomena. It shows the path loss omnidirectional. That means that when you calculate the path loss, you have to combine the different rays that are received from the UAV in this case, and the way you combine them depends on your antenna pattern. So for simplicity, we are considering an omnidirectional antenna pattern. So if you recall, in a previous slide, I said that we classified our 28 gigahertz ray tracing data into two different environments, the Tokyo-Beijing environment and the London-Moscow environment. So what we're doing here is we're trying to test the accuracy of the model, the prediction, within a certain environment. So it's what we call the intra-environment evaluation, and across environments, what we call the inter-environment evaluation. So let's look at the left part of the slide, which considers the intra-environment evaluation. So we see an excellent match because we're comparing the data that we feed to the neural network from Tokyo-Beijing and what the model spits out, and there's a very good match both for aerial cells and for terrestrial cells. Also, if you see, the model is able to capture a dual slope path loss. You see that knee on the CDF on the distribution. That represents the transition from non-line of sight to line of sight links. Okay, now let's look at the figure on the right. This is a little bit trickier. So what we're doing here, we're trying to do an inter-environment comparison. Okay, so we have the same curves as on the left, so the data from Tokyo-Beijing and the model from Tokyo-Beijing, and then we have what the model produces for London-Moscow. So imagine that we train the neural network on data from London-Moscow. We create a model, and then we want to plot the path loss from that model. So there's clear divergence. So actually, for the terrestrial case, there is no divergence. The path loss has the same distribution. It doesn't matter whether you train your model on Tokyo-Beijing or London-Moscow. But for aerial cells, there is a difference. You see, there's clearly a mismatch. And why is that? This is because of the link state prediction. So we actually further investigated that. We plot one more curve, which is what is labeled as London Moscow path mode only. So what we did there is this time we give the correct link state prediction, but we still use the model trained on London Moscow. In that case, there's a perfect match. So that means that the culprit, if we want to call it like that, is the link state prediction. We already saw that the density and the height of buildings was very different in the two cases. So it makes sense that if we use one model or another, there will be a difference in terms of the probability of line of sight. So that means that if we use the London Moscow case, then the probability of line of sight will be overestimated because there are fewer high-rise buildings, and this is exactly what we see in this plot. So let me keep going with some other interesting results. Here I'm showing you the angle distribution both from Tokyo Beijing and London Moscow. Same conclusions can be taken from the two different environments. So we have side by side again the data and what the model produces, and we have mixed terrestrial and aerial cells in this case, but we have four different angles. We have the azimuth of departure, the elevation of departure, that is at the UAV side, because the UAV is transmitting in our setup. Then we have the azimuth of arrival and the elevation of arrival, which is at the base station side. So we see that once again the model matches very well the trends in the angular distribution. We also see that as UAVs and base stations are further apart, meaning we increase the distance, then there would of course be less local scattering because they're further apart, and there will be therefore less angular spread. In particular, this is true at the base station side. So we see that the angular spread is decreasing. Also, we see that there's a wider azimuth spread versus elevation. This depends on the configuration of the buildings. And we also know that because the UAVs are often elevated with a minimal local scattering, especially when they're high, they have a minimal local scattering. So there's a much greater scattering at the base station side. So that means that the angle of arrival, because again, we are assuming the UAV is the one transmitting. So you can see this in the plots. The angles of arrival, both azimuth and elevation, have a much larger spread if you compare them to the angles of departure. This is true in both environments. So the model is able to learn all these real-world phenomena. So let's move to the calculation of SNRs. In this slide, I'm showing you the median SNR for aerial and terrestrial cells. This is the SNR predicted by the model, and it's plotted as a function of the horizontal distance and the elevation of the UAV. This is done for the Tokyo Beijing environment, but the same could be shown for the other environment. So what can we see in this case? Well, we see that aerial base stations provide greater coverage at large horizontal distances and at large UAV heights. In general, aerial base stations provide a better SNR. Terrestrial base stations may surprisingly provide coverage at small distances. So if you observe the plot for terrestrial for less than 100 meters, the SNR is actually good. This is quite surprising. Why? Because such SNR is not due to the vertical direct paths only, because terrestrial cells are down tilted, and there's a very big difference in the front to back gain, about 30 dB. So that means that such a good SNR cannot be only due to the direct path, but probably there are additional paths due to scattering through the ground and reflections from buildings that add up constructively and help provide coverage. We'll see this phenomenon better illustrated in the upcoming slide. Okay, so bear with me because I'm going to show you what I meant in the previous slide. In this case, I show you the actual distribution of the SNR, not just the median, and for the setup illustrated on the left. So let's see what I'm talking about. I have two different cases. One considers a terrestrial base station in red, and one considers an aerial base station in blue. In this case, the aerial base station is sectorized and facing up. Okay, so the terrestrial is down tilted as usual by 12 degrees. The aerial one is up tilted by 45 degrees, okay? So we position the drone somewhere at 120 meters on the x coordinate and at 120 meters in the elevation, okay? So we want to see what the distribution of the SNR is. So let's look at the plot now. So we see different things. So first of all, we see clearly a transition between non-line of sight and line of sight regimes. The red case again is for the terrestrial cells and the blue case is for the aerial cells. So we see two main phenomena here. First, the aerial base stations have a better antenna gain. If you see the knee on the CDF, for aerial base stations it occurs at about 40 dB, and for terrestrials it occurs at about 30 dB. So there's a better gain for aerials. This is due to the antenna gain. Of course, aerial cells are up tilted at 45 degrees, so for that configuration they get a better antenna gain to the drone, right? Also, aerial cells have a higher line of sight probability. If you see the transition from non-line of sight to line of sight in the red curve occurs at 0.4. That means that 60% of the cases we are in line of sight. And for the blue one, it occurs at about 0.15. That means that in the 85% of the cases we are in line of sight. That also makes sense because aerial cells are elevated, they are on rooftops, and therefore they are more likely to have an unobstructed path to the UAV. But there's more than that. So in this slide, we show the same thing, but now the drone is on top of the cells. So now the x coordinate of the drone is 0. That means that there cannot be any buildings between the terrestrial cell and the drone, or the aerial cell and the drone, okay? So let's look at the CDF of the SNR again. Obviously now the probability of line of sight is 1. That's why there is no line of sight behavior. However, we see that the red curve keeps increasing after the line of sight spike that occurs at about 18 dB. So we observe two things. First of all, again, the blue curve has an advantage over the red one. So aerial cells have an advantage. Their line of sight path is stronger. Why is that? Well, then again, because they're facing up, so they have a better antenna gain towards the drone. However, there are many terrestrial base stations that have not only a line of sight path, but also no line of sight paths. And some of these add constructively, so through reflections from the ground, for example, or other buildings, and they keep increasing the SNR. And some of them actually play a very strong role because they can even provide an SNR that is better than the one achieved by up-tilted base station. So this is a very interesting phenomenon that we observed, which says that reflections can actually be helpful and assist terrestrial cells in reaching UAVs even when they are not on the main lobe, which that is never the case because of course terrestrial cells are down tilted. So what's the way forward? So the ultimate objective for this channel modeling approach is to train our neural network with measurements. We will find that very valuable. So our channel modeling approach is publicly available, so we encourage anybody who has UAV millimeter wave measurements to feed our model and produce to feed our network and therefore produce a very useful model. Also, deployment studies are much needed because one should determine what's the capacity with a 5G new radio rollout of millimeter wave terrestrial base stations. That means let's not only look at coverage and SNR, but let's also study the interference and whether high capacity links can actually be supported for drones, up to what extent. We would also like to quantify the benefits in a better way of having rooftop mounted aerial base stations, and we think that one should design the sector appropriately of these aerial cells, and the optimal sector design would depend on several factors. For example, the intersite distance, meaning the density of deployment of these rooftop mounted aerial base stations, so depending on how many one can afford to deploy, and obviously the UAV height. Depending on the height of the drone, different up tilt angles might be preferable. So if you're interested in this line of work, here I'm listing some key references, And reference number 3 refers to the actual channel model, which is publicly available on GitHub. So looking ahead, what should we expect for 2030? Here I'm listing in a speculative way some use cases and requirements for 6G for UAV cellular communications. So of course I would expect the same use cases as in 5G new radio, but with many more UAVs as they would proliferate in the sky, and also more demanding use cases for UAVs as radio access nodes, meaning base stations or relays. But not only that, people are talking a lot about the so-called 3D aerial highways, so flying cars as a way to reduce congestion in megalopolis and to save on fuel. Actually, it seems that there are over 100 cities around the world working on what's called urban air mobility, right? So for this, we will probably need hyper high data rates, lower latency, which could be achieved by sending, for example, non-compressed videos. Okay, so we will need very high data rates for that, and obviously ultra reliability when we talk about urban air mobility, with coverage everywhere on a 3D environment, and also with very accurate localization. So given those very demanding requirements and those very appealing use cases, what technologies could enable this? This is also speculative, but we have an idea of what to expect in 6G. And on this slide, I'm listing four ingredients that could be actually relevant to UAV cellular communications in the next decade. I'm listing non-terrestrial and satellite communications because I think that they could be useful in providing, for example, backhaul links to UAVs when UAVs are used as radio access nodes. I'm also listing cell-free architectures because they could be the key to achieve interference relief. So when high drones are highly interfered by other cells, well, this might not happen if we deploy a cell-free architecture. Also, it could be a valid alternative to massive MIMO. It could provide microdiversity, which could help reach ultra reliable and low latency communications. So another very hot topic at the moment is the one of reconfigurable intelligent surfaces. So we could imagine, for example, a future smart city scenario where these surfaces are real-time remotely programmable and they can provide that reliability and everywhere coverage that we are expecting. So once again, terrestrial base stations are down tilted, they are optimized for ground uses, so maybe we can leverage these surfaces to further improve coverage up in the sky. And what about terahertz communications? Well, for use cases that require extremely high rates, for example, a point-to-point backhaul to UAV radio access nodes, then we could consider the very large bands available up in the frequencies. Also, UAV to UAV links could be benefiting from that, but of course there would be big problems if we start considering the effect of UAV wobbling, jittering, and other impairments. They could make this quite challenging. And in all of that, AI could be considered as a very powerful tool for channel modeling. For example, the difficulty of channel modeling is been increasing with the addition of new frequencies, new nodes, like in the case of UAVs, etc. And also artificial intelligence could be instrumental for network optimization and for mobility management. So that's all for this talk. It's been a great pleasure to tell you a brief story of UAV cellular communications. If you have questions or feedback or you would like to collaborate, please do not hesitate to get in touch.